famous intellectual by the name of Sherlock Holmes. And it says, when you have eliminated all that is impossible, which, by the way, sometimes takes 5 years, when you have eliminated all that is impossible, whatever remains must be the truth, no matter how improbable. The thing I'm going to tell you tonight is one of those things which seems nutty, it seems wildly improbable, but it wasn't just something that some of us, I wasn't alone in saying this, that some of us just said, oh, one day, maybe the world is a hologram. That's not the way it happened. The way it happened was exactly this way. When you eliminate everything that's impossible, whatever is left over must be the truth. So let me tell you a little bit about where we're going. Good. Okay. What is this thing which Sherlock Holmes might have eventually concluded after trying everything else? And the answer is that in a certain sense, in a certain peculiar sense, the world is a hologram. Now, not everybody knows what a hologram is. The drain is sucking water out at a sufficiently rapid rate that there happens to be a distance, represented by the red line here, at which the inflowing water is moving with the speed of sound. And as you go in even closer than that, it's moving even faster. What happens to a fish? Let's call her Alice. Poor Alice has passed the point where the inflowing water is falling faster or moving faster than the speed of sound. It's also moving faster than she's allowed to swim. She's stuck. Nothing bad happens to her when she crosses this place. She probably doesn't even know it. You know what it's like? It's like rowing down Niagara Falls and passing the point at which you can't row faster, but you don't realize it. Nothing bad happens to you yet. Nothing bad happens to Alice when she crosses the point of no return. Let's call it the point of no return, but nevertheless, she's doomed. Her friend Bob is on the outside, and Bob is waiting to hear from Alice. Alice has been calling to him, maybe saying, help, help, help. But after she passes the point of no return, not only can't she swim out, but her sound waves that she tries to send a message with are also pulled in faster than the speed of sound, and so she becomes permanently disconnected from the outside. She cannot get a message out, she cannot swim out, and so as far as Bob is concerned, poor Alice has disappeared out of the world. Well, that's about what a black hole is. A black hole is a kind of inflow. It's a kind of place where space itself is falling in. At a certain distance out, it's falling in so fast that to get out beyond it, you would have to exceed the speed of light, the local speed of light. And if you pass that point of no return, again, nothing bad happens to you, but you're doomed. Okay, so I've put this in a couple of, is lost to the outside world, all of her bits and pieces. When I use the word bits, you might think about information bits, if you like, but all her bits and pieces are lost. And the horizon is a point of no return, but it itself is harmless. The place which is harmful, at the center of the black hole, that's called the singularity, but we're not going to be even interested in the singularity. All right, now let's move on to another subject. Of course, we're not really moving on to another subject. We're going to examine a few related subjects and then put them together. Information. Now, information, whatever it is, we'll talk a little bit about what information means, but information comes in bits, in discrete units. Let me give you an example of some information. A sentence. King Canute had warts on his chin. I don't know if King Canute had warts on his chin or not. It doesn't matter. This sentence here expresses a certain amount of information. But when information physicists, information theorists, when they talk about information, they're really not even talking about the meaning of the information. The meaning doesn't count. What counts is the symbols. This is a sentence, or a bit of, or not a bit of information, but a collection of information which consists of the sequence of letters. Whether or not you can read English and decipher it is not the important thing. The important thing is it takes a certain number of letters to describe it. you could convert the message to Morse code. Morse code is, of course, dot, dot, dash, dot, dot. And in converting, this happens to be if you leave out the symbols that you need to put the spaces between the words, this sentence here is a 65-bit message in Morse code. And the real information is in the sequence of pluses and minuses or dots and dashes. This process of going to Morse code has replaced the sentence by a collection of bits. A bit is a dot or a dash. That's what it stands for. It's the same concept as in your computer, except in computers we talk about bytes. Byte is 8 bits. Megabyte is 8 million bits. So this is the same concept that you use when you ask how much storage space you have in your computer. Now let's go to the minus first law of physics. Why is it the minus first law of physics? Well, the first law of physics, there are at least 2 first laws of physics already. One of them is thermodynamics, the other is Newton's. So I didn't want to call this the first law of physics. It's more important and deeper than either of those 2 first laws of physics. There's also, because people realized there was a deeper law, they defined the 0th law of thermodynamics. So the 0th law was also used up. But there's an even more fundamental law. So what could we call it? The minus first law of physics, I will call it. Now, of course, it may turn out that Dick will discover the minus second law of physics and so forth, but at the moment, this is the deepest law of physics I know, and it's that bits of information are indestructible. The meaning of that is that distinctions between situations, distinctions between configurations are never erased. They never disappear from the world. Let me give you an example. Here's again the 65-bit message, but now it happens to be stored on my computer screen. Well, it doesn't matter whether it's on the computer screen. It's buried somewhere in the computer memory, and it consists of a bunch of on and off switches, and it's a 65-bit message. Can you erase some of the message? Can you get rid of a bit? Can you erase a bit? Well, of course you can. If you couldn't erase some of your computer would very quickly fill up and you wouldn't be able to put anything new in it. So you have to be able to erase information. But when you erase information, in fact, you're not really erasing it. You're ejecting it out of the computer by one means or another into the environment. The result is, the environment may actually be part of the computer. It might be the plastic of the computer case or so forth, or it might actually be the atmosphere. When you eject a bit in that way, the indestructible bit, which cannot be destroyed, when you eject a bit, it adds a little bit of energy to the environment and thereby heats the environment. That is why your computer has to be cooled. Your computer has to be cooled because whenever you want to erase information, the bits are little bits of not only, as a matter of fact, they're not only bits of information, they're also bits of energy, and therefore you have to cool your computer whenever you erase. But the lesson here is that bits are indestructible. Information is forever. Well, now we have a very funny little paradox. On the one hand, the minus first law of physics says that bits are never erased. On the other hand, when Alice crawls into the black hole and falls behind the horizon, as far as Bob is concerned, her bits have disappeared from the world. So in effect, for all practical purposes, for all physics purposes, Bob sees a world in which information is erased. Can this be right? This was Hawking's central point in 1976 when he created something that came to be known as the information paradox. It was an extremely deep observation. It was a very important observation. It is not important that Hawking didn't get the right answer. He asked the right question, and this became a central debate, a central question that took basically 20 or 25 years to resolve. We now know the answer, and we'll come to it. The answer is that bits of information never are lost, but nevertheless, the things that came out of the question is so deep that one can hardly say that it was Hawking's mistake. It was one of the deep observations about physics that led to great things. Okay, so you might say, wait a minute, wait a second. The bits Alice's bits fell into the black hole, and there they are, they're in the black hole. Maybe you can't get access to them. It's not too different than locking him in a room and throwing away the key. We don't say that information is lost then, but to make things even more confusing, and this was another discovery of Hawking's, an earlier discovery of Hawking's, black holes evaporate. They disappear. It's as if the box that you hid some information in, after a while, disappears. How that evaporation takes place is not so important. Basically, anything evaporates. Everything evaporates. If you give enough time, little pieces of it break off and disappear into the atmosphere. And if I were to just draw or to use my extremely crude computer skills to try to make a movie of a black hole evaporating, what does it evaporate? It evaporates photons, light, gravitons, other kinds of particles, and as it evaporates, it loses energy, and in the process of losing energy, it shrinks. And it eventually shrinks down to a very tiny black hole, and then it's gone. But when it's gone, where is Alice? Or more to the point, where are Alice's bits? Where are the bits of information that the minus first law of physics says can never disappear? The black hole is gone. Alice's bits could not have gotten out from behind the horizon. Why not? Because to get out from behind the horizon, they would have had to exceed the speed of light, just like the fish would have to exceed the speed of sound. And so we have a real dilemma. We have a conflict of principle. On the one hand, black holes seem to erase information. On the other hand, the most basic law of physics that I know says that information is never erased. Next, what is entropy? You've all heard the word entropy, and you probably heard that entropy has to do with confusion, and entropy has to do with chaos, and entropy has to do with the world coming to an end because everybody gets too confused to tie their shoelaces or whatever. But entropy has a very distinct meaning, so let me tell you what it is. Here I've imagined a bathtub full of water. Just to get away from black holes for a while, let's think about a bathtub full of hot water, or warm water, and how much information do we need to know about that bathtub full of hot water? How much information is there? And how much do we need to know in order to know whether we should step into it and take a bath? Well, really, there's about two things that we really want to know. We want to know whether there's any water in the bathtub. So we want to know the volume of water that's in the bathtub. That's important, how much water is there. And the other thing we want to know is the temperature of the water. Right? When you get in the bathtub, you want to know the temperature of the water. Okay? That's about all. That's about all the information you need. That's about all the information that would be easy to get. How much more information is there about that bathtub full of water? Well, the answer is a huge amount, an enormous amount of information. The physicists all know that. And what is it? Well, if you looked at the water through a microscope, you would, of course, see molecules. The position and velocity of every one of those molecules is information. That information may be extremely inaccessible. Let's call it hidden information. Why is it hidden? It's hidden because it's stored in a huge, huge number of degrees of freedom, many, many too many to take account of, and they're too tiny to see. That's all. So, yes, the bathtub has a huge amount of hidden information. Hidden, as I said, because it's stored in things which are too small and too numerous to keep track of. That's what entropy is. It is simply the information that's hidden, usually for the reason that I said. But for any reason, if information is hidden from you, we call it entropy. That's all that entropy is. What was extraordinary was that sometime around 1972, a young physicist by the name of Jacob Bekenstein, this is not a picture of Jacob Bekenstein in 1972, but Jacob Bekenstein was a student, and he announced black holes have entropy. What did that mean? That meant that black holes have in them hidden information. Well, that's not surprising. There's no surprise in that. Of course black holes have hidden information and stuff. That's exactly what black holes are. They're a place where information falls in and it gets hidden. You can't see it when it's behind the horizon of a black hole. But the real importance of what Bekenstein did was to be quantitative and say how much hidden information is in a black hole. What is the maximum amount of information that can be hidden inside the maximum number of bits that can be hidden behind the horizon of a black hole? Here is the way he approached it. I'm going to tell you, just rough it out for you, how he approached the problem. I'm not going to do the calculation for you, but I'm going to show you what he did. He asked a question which is pretty similar to the following. Supposing you want to know how many atoms it takes to fill up a bathtub full of water. Well, there's a simple way to do it. You drop in one atom at a time, and you count how many it takes until the level of the water is up to where you want. You know what the answer is going to be. The number of atoms, or the number of bits, or the number of drops of water is going to be proportional to the volume of the bathtub. Right? If you double the volume of the bathtub, you'll have to put in twice as much water, and therefore twice as many atoms. Right? So that's the kind of usual thing. What Bekenstein did is he said, let's actually count how many bits of information it takes to drop into a little tiny black hole in order to build it up to a large black hole. So he said, oh, let's start with a tiny black hole. A tiny black hole is practically no black hole at all. A tiny one, as big as a peanut. Well, a peanut is in fact actually a gigantically heavy black hole, about as heavy as the Earth. Let's start with a lighter one that's about as heavy as a dust mote. And that's about the smallest black hole that you can have. And drop a bit of information into it. Now, what does a bit of information mean? A bit of information means an elementary particle. It could be a photon. Let's say a photon. We drop one photon in, and the only information is that we dropped the photon in. Or perhaps it's the information that we dropped a photon of one polarization instead of another polarization. But we drop an elementary particle. Now, there's a deep thing going on here, that information in quantum mechanics comes in discrete units, and they're called particles. So what Bekenstein did is he said, throw in a particle, throw in a bit. The effect will be to increase the energy and therefore the mass of the black hole, and the black hole will grow a little bit. Do it again. Drop the second drop in. Black hole will grow a little more. Do it again. Do it again. Until the black hole achieves the size that you're interested in. And count how many photons of the appropriate wavelength does it take to build the black hole of an appropriate size. What did Bekenstein find? I wonder if there's another one after this. No. What he found, well, first, what was the natural expectation? The natural expectation would have been that just like the bathtub where the number of drops of water is proportional to the volume, the natural expectation would be that the number of bits of information that it takes to build a black hole of a certain size would be proportional to the number of cubic meters or number of cubic kilometers or whatever it is, the volume. That is not what Bekenstein found. What Bekenstein found was that the number of hidden bits of information in the black hole is equal to the area of the horizon measured in a unit called the Planck unit. First of all, that was very surprising, that it was area and not volume. What it meant was that when the bits of information fall onto the horizon, they behave as if they were little impenetrable objects which collected on the horizon and simply couldn't push each other out of the way and achieved some density, almost as though you had a bunch of coins on the table and you tried to pack them in as tightly as possible, but on the horizon and not in the interior of the black hole. So that was the first surprising thing. The other surprising thing, well, it wasn't surprising at that point, but it might surprise you, that the size of one of these little bits, in other words, the area occupied by one of these little bits, is very, very small. One Planck area. Planck does not mean board. It's the name of the famous physicist Planck, who has a constant named after him called H. G here is Newton's gravitational constant, and C is the speed of light. And if you work it out, it's 10 to the minus 66 square centimeters. It would take about 1,000 trillion of these little Planck areas to wrap a proton, to wrap the surface of a proton. So this is a very, very small unit, but nevertheless, it's a discrete little unit. And this is what Bekenstein calculated from the combination of quantum mechanics and properties of black holes. This was interesting. Now, you could ask about a bathtub full of water. A bathtub full of water has an entropy. It means it has hidden information. What is that hidden information? Well, we know now, today. It was not known, incidentally, around 1900. It was not known for certain that it was atoms, the motion of atoms, the positions of atoms, which made up the entropy of a bathtub full of water. In fact, it was Einstein who nailed that concept in place ultimately. But you could ask the same question about the black hole. If the black hole has entropy, it means there are hidden, tiny, microscopic degrees of freedom on the horizon, which we don't know about, which are somehow making up that